This video is going to be a review of redox balancing, and part of that is usually oxidation numbers. But really what I'm doing is I'm reviewing oxidation numbers because you haven't seen them in a while, and it's one of those important skills that you know as you get ready and study for your final exam that comes at the end of the semester. So, oxidation numbers or oxidation states are a representation of electrons lost or gained by elements in a compound, and there's really just a few rules that we have. So if it's a free element, pure element, right, its oxidation number is 0, and I just called it ON or on. So copper, Cl2, those are all examples where the oxidation numbers are 0. Now, if it's a monatomic ion, then the oxidation number is just whatever the charge is. So for iron 3 plus, it would be 3, and for O2 minus, it would be minus 2. Now, one of the other important rules to recognize is that when you are trying to find the charge or the oxidation state of an element in a compound, one of the important rules is that the oxidation numbers always need to sum up to 0. That's for compounds. Now, you have to remember a compound's different than an ion because basically ions have charge. And so really the rule is that the oxidation numbers always add up to be the overall charge. So in the case of compounds, that charge is 0. But for ions like sulfate, for example, the overall charge, right, the minus 2 of the sulfate ion, is actually what you get when you sum all the oxidation numbers up of the elements that make up sulfate. There are also a couple other rules, and these are actually the slides I use for my Chem 1A class. But basically, fluorine has a minus 1 charge because it's the most electronegative element on the periodic table. Oxygen is almost always minus 2 unless it's with another oxygen. So, in other words, it can't outcompete itself for the electron to get the minus 2 charge. So in H2O2, it turns out each oxygen's oxidation number is actually minus 1. Now halogens are generally minus 1 unless they're with something that's more electronegative than them. So for example, if you look at chlorine, like Cl, right, and it's bonded to fluorine, well, this has got to be plus and this has got to be minus because the fluorine has more electronegativity and draws the electrons closer to itself. The same thing is true for oxygen. Other than fluorine, oxygen has a higher electronegativity than all the other halogens. And so if it's let's do this, OF2 like this, right? Then oxygen's actually plus 2 in this case, and each fluorine's minus 1. But if it was OCl2, then oxygen's still minus 2, and each of the chlorines is plus 1. Now, like I said, this overall charge has to add up to be 0, so the chlorines are plus 1 each because there's 2 of them, and then the oxygen takes this traditional minus 2 charge. So really, when it gets right down to it, you look at which elements are bonded together, and the one that's more electronegative gets the negative oxidation state, and the one that's less electronegative gets the positive oxidation state. So some examples are written along the side here. For group 7A, 7A would be the halogens. Their oxidation number is usually minus 1. So in the compound like CCl4, they each take a minus 1 charge, and then the carbon has a plus 1 charge, for example. And NH3, right, the nitrogen is more electronegative than the hydrogen, and as a result, group 5A generally is a minus 3 charge, or nitrogen's usually minus 3. When it's bonded to a hydrogen, the hydrogens have plus 1 each, and then the nitrogen will have a 3 minus charge. So let's practice and do some oxidation numbers in a couple of different polyatomic ions. So for the sulfur in S2O3, the way we calculate the oxidation number is S, right? And this is how I'm going to do it. I'm going to call that 2x because there's 2 of them. And I'm going to say plus 3 times minus 2. That's for the oxygen, right? And then that's going to be equal to minus 2, like that. So then I have to do the math and figure out what the charge for sulfur is. So what I'll do is I'll say 2x plus minus 6 is equal to minus 4, like that. And, oh, sorry, minus 2. I don't know where I got minus 4 from. Minus 2. And then I'm going to add 6 to both sides. So I'll get 2x is equal to 4. And each sulfur has a 2 plus oxidation state, if I did my algebra correctly. Now in S2O8 2 minus, we would do the same kind of thing. I'll use a little more space here this time. So I have 2x, right, plus 4 times minus 2. Again, oxygen's with an element that's less than electronegative, so it takes its traditional minus 2 charge. Oh, it's 8. I don't know where I got 4 from. Goodness. There we go. And then that's going to be equal to minus 2. So then I've got to do the math. That's minus 16. Like that, right? Is equal to minus 2. That's 2x. So 2x is equal to 14. And x is equal to 7. So each sulfur in that compound has a plus 7 charge. Okay, so next we're going to look at oxidation-reduction reaction. So what I want to do really quick is we're going to do some oxidation number calculations, and we'll figure out what's being oxidized and what's being reduced. So for iron, it has a 0 charge here. And for oxygen, these also have a 0 charge because it's in its pure elemental state. So because it's not bonded to something that's less electronegative, it doesn't take a negative oxidation number, right? But in Fe2O3, iron, a metal, is generally less electronegative than oxygen. We then assume that oxygen has a minus 2 charge here, and that the iron, we can calculate its oxidation state by saying overall charge is 0, right? So it can be 2x plus 3 times minus 2. That's equals 0. So what that means is each iron is a 3 plus charge when you do the algebra for that. So iron is going from, pen does not want to stop as I'm trying to swipe with my finger. Iron is going from 0, right, to plus 3. So each iron is losing 3 electrons. And then the oxygens, didn't really leave myself much choice there. I'll have to use a different colored pen here. Let's do this. Each oxygen is going from 0 to minus 2. So that means it's gaining 2 electrons. Now, if you remember what we said before, that in an oxidation-reduction reaction, the number of electrons running the oxidation pathway, which is this one here, and the number of electrons going the reduction pathway, which is this one here, need to be balanced. So how is this balanced? Because I got 3 here, right? And I got 2 here. So you'll notice that there's 4 irons here, right? So that's 4 times 3, so there's 12 electrons along that pathway. And then on this one, there's actually how many oxygens, right? There's 6 oxygens, each times 2, so 6 times 2. That's going to give me 12 electrons as well. So on this pathway, 12 electrons are going into oxygen, and on this pathway, 12 electrons are leaving the iron in our balancing of our reaction. And so it does actually work out. Even though when you look at it initially, you see a minus 3 and a plus 2, the number of electrons going through the redox reactions for the oxidation and the reduction are balanced. Now, just keep in mind, right, the iron is being oxidized because it's losing the electrons. And let me write that down, oxidation. And then the oxygen is being reduced because it's gaining electrons, right? Because it went from 0 to minus 2 in this compound. So here's another redox reaction that people aren't always considering as redox reactions, because you basically don't have to balance them using redox methods. But those are combustion reactions, and in combustion reactions, oxygen is usually the oxidizing agent, which means it gets reduced, and then whatever else it's reacting with becomes the reducing agent. So provides the electrons. So what we're going to do is really quickly calculate the oxidation numbers in this reaction, and then show like how the electrons balance even in a combustion reaction. So carbon in this compound, this is octane, right? So in octane, what we want to do is calculate the oxidation number of carbon. So we'll go like this. I have 8x, and I'm going to go ahead and write it like this again, plus 18 times 1 plus, like that. And again, carbon's actually more electronegative than hydrogen, so hydrogen takes on its traditional +1 charge. It's a compound, so we're going to call that 0. And then we're going to go ahead and solve this. Then we have 8x is equal to minus 18, so x is equal to minus 18 over 8, which comes out to be 2 1/4. And you're like, but I thought this was the number of electrons lost or gained, or how many electrons, were gained by the carbon in forming the octane. And it is, but the thing you have to remember when you're doing calculations like this on larger compounds, lots of times you have different oxidation numbers for elements in a compound, and then so it doesn't come out to be like a nice round number. But it's okay. This is not like unusual at all. Now, so oxygen will be the oxidizing agent most of the time, which means it's going to pull electrons off and become carbon dioxide, pull electrons off the carbon to make carbon dioxide. So oxygen over here is 0. We said the carbon in the octane is minus 2.25. So now we need to go to the other side, and in carbon dioxide, right, oxygen is a minus 2, so we know that this is plus 4, because there's 2 of them, right? So that needs to balance to be 0. And then over here, we don't really need to worry about what's going on over here. We're just looking at oxidation numbers. In H2O and in CO2, the oxidation number of the oxygen is minus 2. So what's going on with the oxygens, right? Like here, well, we're losing, or we're gaining 2 electrons. So there's 2 electrons here. And then the carbon going like this, well, I'm going from minus 2.25 to 4, so that's a loss, right, of 6.25 electrons. Again, the number's weird, but that's okay. All right, now, this is where it'll all come out to be nice and round numbers. We're going to calculate the total number of electrons that are going through this pathway. So I have 25 times 2 oxygens, right? So I'm going to take this, and I'm going to multiply that by 50. There's actually 100 electrons being gained by oxygens, which means there has to be 100 electrons lost by the carbon, even though it's like 6.25. Let's hope this works out, right? So what I need to do is I need to multiply that by 2 times 8, or 16. So I just pulled out my calculator so you can believe what I calculate here. 6.65. I don't know, I get these weird numbers from times 16. Hey, look at that, it's equal to 100. So I guess it actually works. There's a lot of electrons going here, right? So the octane is giving up 100 electrons in this balanced equation, and the oxygen is gaining 100 electrons. But again, combustion reactions are redox reactions. And when I did the 100 electrons for the 50 oxygens, right, I do have an arrow just going to here, but it's actually going to here and to here because it's a balanced reaction. That's where all 100 electrons went to. It went into 2 different compounds. Okay. With that, we're going to talk about the half reaction method for balancing redox reactions. There's also another method, it's called the redox number, and really I think this is mostly historical, why you learn oxidation numbers, and then all of a sudden they tell you need it to balance reactions, and then you do the half reaction method and you never really needed to know the oxidation numbers, is because there used to be another method that people used a lot. It's called the oxidation number method, and that's actually a really nice way to learn how to balance redox reactions. But we're not going to be covering it in this section of the class, so I just thought I'd tell you that's kind of the reason why it seems weird. Everybody tells you need to know oxidation numbers, and then they tell you that you're going to need them to balance reactions. It turns out you never use them. So anyways, but if you want to know how to do it, I can show you. It's actually kind of fun. Anyways, balancing this reaction, the thing that you have to remember when you're doing these redox reactions is it's a very systematic method. You're going to take the reaction and split it into what we call half reactions, and then you're going to do the same thing to each half reaction. So I'm going to show you on this one at least some of the process, and then I actually have it all kind of worked out. We're going to work it all out on the other slide, but this is just to show you how the rules work, right? So the first thing is to identify half reactions, and identifying half reactions is fairly simple. I have aluminum. It's not going to make sulfate or sulfite or thiosulfate. It's going to make aluminum, and sulfur must be making thiosulfate. So that's how we identify. We just look to see the composition of the substances, and we put like things together. So I'm going to go like this. Aluminum makes Al3 plus, and then I'm going to down here write SO4 2 minus makes S2O3 2 minus. Now, the first thing that you're going to do is you're going to balance anything that's not hydrogen and oxygen. Now, in the case of aluminum, there's nothing to do. But in the case of sulfate, the thiosulfate, I have to balance the sulfurs, and so that means I'm going to have to drop it. I'm going to have to drop a 2 right here. And that'll balance the sulfurs. And we're not worrying about the oxygens and the hydrogens until after we do that step. Now, having said that, the next thing you would balance is oxygens by adding water, hydrogens with H+, and then charged with electrons. Now, in the case of the aluminum reaction, there's not much to do because there is no hydrogen and oxygen. So all we're down to is dropping electrons in. And so we're going to drop the electrons in like this. Okay. Now, with the sulfate to thiosulfate, now that I have the sulfurs balanced, right, we're going to go through this process of adding oxygens by adding H2O. Now you'll notice I have 8 here and I have 3 here, so that means I'd have to add 5 on this side. And then we do the hydrogens. And I hope you can see the logic in the process. In the process, we do the H2O first because we're going to add hydrogens. If we did the hydrogens first, we'd have to come back here and add more oxygens as H2O, etc. And you sort of would just go round and round and round. So we're building up in a process where we do the oxygen and then the hydrogen, and then we'll do the electrons. What will happen next then? It's the same thing that happened all the way over here. I just said, oh, I have 2 electrons here. I need 2 electrons here, so I doubled this reaction, right? We're going to get the electrons to balance between the half reactions. So that's this step here. So whatever electrons I have here, I'm going to balance it with the electrons that I have here. And now, if that kind of sounded familiar to you, actually it is the same process that you use when you first learn how to write chemical formulas. I want to get charges to balance as I put them together, and really when you're balancing charges, you're balancing electrons lost and gained. And so what did you do? Well, you'd normally take this by 3 and this by 2. You'd cross multiply and you'd end up with Al2O3. Well, that same process is what's going to be happening between 2 reactions now, and just not just in a compound, right? Now, then the last step that you do for many reactions is just to add the two reactions together and get rid of the excess material. And if you're balancing in a base, and this will be clearer later when I do it, you're going to add the self-ionization of water reaction so that you can get hydrogens to cancel, and that'll leave you OH minuses, and effectively that says that the reaction is balanced in base. So let's go ahead and follow those rules, and I like doing it in a kind of systematic way. I'm going to go ahead and do the aluminum one. I'm just going to write it like this because we already did it and there's not much to it. But then what I do when I'm teaching this, especially in Chem 1A, is I actually separate all the steps. And it doesn't hurt to just say, okay, I'm doing this. I'm going to do 1, 2, 3, 4. Those are my steps, right? So in step 1, I'm going to do this. So I'm going to be doubling my sulfate by multiplying it. So then I have, 2 in front of the SO4 2 minus. So then the second step is to balance the oxygens with water. And then at this point, you can actually make little notes to yourself, like, okay, I have 8 here, but I only have 5 here, or 3 here, sorry. So I'm going to need 5, right? So I'm going to add 5 waters to it, like this. And then the third step is to go ahead and balance the hydrogens. Now, I didn't have any hydrogens in either side when I started, so I have 10 here. So I have to add 10 hydrogens. So I'm going to go 10 H pluses. And this is, again, where you might want to make a note. And the note for this one is what the charges are. So I have -4. And sometimes people, students will write the notes on the outside. That's fine too. But it's -4 and +10. So that leaves me with +6 overall. And on the right side, I have -2 and 0, because these are 0, right? So I have -2 and 0. So now I'm at -2 like this. So in order to get the electrons to balance, what I need to do is I need to add the electrons to the side that has a more positive charge. And so in this case, I need to go from 6 plus to -2, so I need to add 8 electrons. Now, I'm just going to add everything up now. So I have 2 SO4 2 minus plus 10H plus 8E minus, like that. And that's going to give me S2O3 2 minus plus 5H2O plus, am I missing something? I think that's it. So now you double check, right? I have a -2 charge here. I have 8 negatives here. And then I have 4 negatives here. So that's -12, right? Plus 10, so that balances my charge. So that's good. I have 2 sulfurs and 2 sulfurs. I have 8, right? 2 times 4, 8 oxygens. Here I have 3, and here I have 5, so that's 8. I have 10 hydrogens, and I have 10 hydrogens. So this reaction's balanced both in charge and in mass, like it's stoichiometrically balanced. Now what I need to do is combine these two reactions. So what I've done is I've balanced the half reactions, and now I'm going to recombine the half reactions to balance electrons. So when I'm looking at this first reaction, I have 3 electrons. On the second reaction, I have 8 electrons. So I have to cross multiply. Multiply this reaction by 3. and I'm going to multiply this reaction by 8. Now, when I do that, let's see what happens, right? I'm going to have 6 SO4 2 minus plus 30 H plus 24 electrons. That's the common factor that I was shooting for to get to balance. And then I'm going to have 3 S2O3 2 minuses plus 15 H2Os. And then the reaction I'm balancing it with, and I try to line up my arrows when I do this, is going to be 8 aluminums plus 24 electrons on this side. That's just getting this, plus 8 aluminums on the left, like that. So I'm going to cancel out the 24 electrons, and then I'm going to add these two together, and I'm going to get 6 SO4 2 minuses plus 30 H plus 8 aluminums. I feel like I missed something, but I think I got it all. Makes 3 S2O3 2 minus plus 15 H2Os plus 8 aluminum 3 pluses. And that should be the balanced reaction, and you can always check it. You check it first by checking like the mass balance, and then you also can check the charge. In fact, I usually do like I did earlier. I check the charge first. So 3 times minus 2, that gives me 6 negatives. This gives me 24, so I have a total of 18 positive on this side. And then over here I have 30, right, positives, but then I have 12 negatives, so I get a total of 18 positives, so that balances. One of the things I found over the years in balancing these reactions is if you get the charge right, the mass probably follows. It's mostly a matter of being careful. So if you got the charge right, then you probably were careful enough and got the mass balance correct. So we'll balance this one. I'll do the half reactions one at a time. You should pause right before I start balancing each half reaction and just restart, because I'll just have the answer there. You can check your work and they'll balance the overall. So go ahead and pause. That's what you should have gotten on the first half reaction. IO4 2, sorry, yikes, IO2 minus plus 2H2O plus IO4 minus, goes to IO4 minus plus 4H plus 4 electrons. So the other half reaction is the one for permanganate, MnO4 minus, going to Mn2 plus. And one other note, I didn't do that first step. This is actually steps 2, 3, and 4 here. And then the only thing I calculated was the charges so that I'd make sure I added the right number of electrons. One of the things to keep track of, like I had a -1 on both of these up here, and then nothing else here was charged, so I actually just knew to add 4 electrons from that. But let's go ahead and do this one, so go ahead and pause. So that's your half reaction, and yeah, anyways, right, MnO4 minus, I need to add, and no oxygens over here, so I added 4, then I need 8 hydrogens, I added the charge up, this is +7, this side's +2, so I need 5 electrons, so that gives me the overall reaction. Now, we need to combine these. In order to combine them, what we're going to be doing is making sure we can cancel the electrons. So there's 4 here and 5 here. I should point out, I didn't mention this earlier, this is the oxidation half reaction with the electrons over here, and this is the reduction half reactions with the electrons on the left side. So this is the gaining of the electrons, and this is the loss of electrons. So we'll go ahead and go like this then, and multiply the first reaction times 5. Second reaction, I'm going to multiply by 4 to get the electrons to balance. I'll go ahead and write out each half reaction, so you want to go ahead and do that, and we'll add them together and cancel stuff out when we restart the video. So go ahead and multiply these out, stack them on top of each other, and then I'll go through the cancellation of all the extra stuff with you. So I think I did that right. I multiplied this by 5, so I have 5 here, and then 10, and 5, and 20, and 20. Now I multiplied the second reaction by 4, so I have 4, and then 8 times 4 is 32, 4 times 5 is 20, and then 4 and 16. So now what we do is before you add these up, the easiest thing to do is take another colored pen, actually. I do recommend that. Cross out stuff before you add it. It'll be a lot easier. So there's 20 hydrogens. So that leaves me with 12, like that. And all the electrons go away. And so now you can rewrite the reaction as 4MnO4 minus plus 5iO2 minus plus 12H plus. And sometimes I recommend to people circle the stuff like the H pluses, just so you don't lose them as you're adding stuff together, because it's really easy to lose track of stuff. You should catch it as you're double checking, but still it's kind of a pain to miss stuff. Then 5iO4 minus plus 4Mn2 plus 6 H2Os. And again, my standard trick, we'll check the charges, right? So this is 5 negatives here, 4 negatives here, so that's 9. And then I have 12 positives, so that leaves me plus 3 overall. Here I have 5 negatives here, and then 8 positives, so that's plus 3 overall. So most likely this is balanced correctly, even without checking the hydrogens and the oxygens. Now, this is an example of having balanced something, assuming it's under acidic conditions. And you might be asking, well, what do you mean by under acidic conditions? I added H plus, right? So if I want to balance this under basic conditions, go back up to here, and it says add H plus plus 8 OH minus to H2O. That's kind of the self-ionization reaction of water, just written backwards. But basically you're adding water. Now, if I want to do it under basic conditions, that means I have to neutralize all of that. So a couple of ways people do it. I've always just liked doing it like this. This is the reaction I want to use, like this. And I say to myself, well, how many of these do I need to add, right? Well, I need to add 12. So I'm going to go 12, 12, and 12. And then what happens is my H pluses will cancel. Now I have waters again, right, that I can cancel. Again, I do advise, like, get a different color pen when you do these. All those will go away. There's 6, so don't lose track of that. And then I have 12 OH minuses over here. Now, honestly, when you're looking at this then, one of the things you have to really consider, although I won't force you to do this, but you should consider whether or not the products are soluble under basic conditions, because hydroxide generally makes things insoluble. And then rather than having the product be just this, let me write it out. I have 4 right now, MnO4 minus plus 5iO2 minus plus 6 H2Os. I have 5iO4 minus. Technically, what probably happens in this reaction is the manganese precipitates out. So rather than writing this, it's probably technically more correct to write it as this. plus, and then so that takes up 8 of them, right? Plus 4 more OH minuses. That's probably what it really should be. Although most of the time you can stop at this point here and everything's all right. But if you're given the option under basic conditions to balance a redox reaction, and it's, let's say, a multiple choice type question like on your final, then you should probably be looking for possibly the answer looking like this or the answer looking like that.